All right. So last time we formally introduced the MapReduce, and it contains many important concepts, right? The first one is the programming model. So you can see it is a programming model based on divide and conquer, but more specifically, the data handled by this programming model is key value pairs. And you can see that his map function will try to convert each input key value pair to one or a set of intermediate key value pairs. It's depending on the programmer how they would like to extract information out of the data. Okay, and then it will perform shuffle and grouping operations. And its design is because of it's due to the majority applications in their use case. So most of the time they would like to have their results get sorted by the key. So that's why it built in this grouping and sorting operation in this programming model. So it's not a general programming model. Actually, it is a very specific programming model, right? And then after you do the grouping, then all the values of a key will be aggregated by your reduce function, and then output the results. And so you can see that in this process, right? It try to extract, try to separate the concern of what to compute and how to compute. So the how part is, how would you like to extract information? How would you like to aggregate information, right? How would you like to process the information? So that is the purpose of map function and reduce function. So it leave it to the programmer to decide what to compute. And if further, you can see that when you design the map function and reduce function, it's already limited to the case that you only need to handle one record at a time or one key at a time. So you don't need to. It's not from the function point of view. It's not a parallel computation. It's a function that could be independently applied on a single record or a single key. So that's why it can explore or it can provide very high parallelism, right? Because those functions could be applied to those records independently and running on individual machines. Okay, they also simplify in some way, right? The burden of the programmer, because they can just deal with one record at a time without knowing or the having the concept for those all the tedious problem you encounter when you write a parallel programs. Okay, so in terms of the how, right? How to compute, how to enable divide and conquer, or how to manage those computation, how to recover from failure. All those questions those questions are limited to the framework or the MapReduce or Hadoop systems, right? So those problems are you require extended knowledge in parallel computation. So that's why it's already it's separated concern and solved by the framework, not by the programmer, right? So like shuffle here, right? If you have to do this in a synchronous way across a large number of mapper and reducer running on different machines, that's actually a quite complicated case for parallel computation and communication, right? So you don't need to handle, it's not handled by the programmer. You can see it's implicitly handled by the framework already, right? Or how to do the concurrent write to a file, right? It's all solved by or supported by the framework, not the programmer. Okay. Okay, so that's the the intention of this whole solution, right? Try to that people can write a program that can run on a large scale systems like data centers with millions of machines and with some unexpected hardware failures. Okay, so through this framework, through this programming model, they want their engineer can write such code in a very short time frame, right? They can simplify their programming burden. Okay. Okay, so we have this classic word count example to show you how you could convert or create or write a application from using this programming model. And you can see it's not actually not straightforward because the programming model is fixed. So you have to somehow to figure out how could you convert or write your algorithm based on this or under this the constraint of this programming model. So as a matter of fact, it's not guaranteed that any problem could fit into this programming model. Okay, and it's also not guaranteed that any map reduced program you write could efficiently do the computation, because sometimes in order to fit your problem into this programming model, you have to add a lot of other things, or you have to have some redundancy uh, during your during your data processing steps. So all those could make the computation less efficient. However, again, we said that this solution is very much driven by the application. So they are only target on specific application, especially the application that just simply try to most of the time just try to scan through the data, right, and try to extract the information from each of the record and then produce the result based on the aggregated information. So for that case, you can see those kind of use case or application can perfectly fit into this programming model. So that's why you can very easily write the solution, this code, and run it efficiently in parallel in the very large scale data centers. Okay. Okay, so that's why last time we mentioned there are many other things that need to be handled by this framework, and because at this stage you have know how you have learned and write your you have experience writing those parallel program, right, using lower level like library like MPI. So I believe you now have some sense about right how to say implement a dynamic load balancer or scheduler, right? And what kind of synchronization problem could encounter in a parallel program, and what might be the technique to solve that, right? So you should have the knowledge now. The difference for us is not only you should be able to write a map reduce program, but also understand or have idea how the map reduce framework could be implemented, or why how it is designed in this way. Okay, so the only thing you haven't have encountered before is handling the fails, right, or faults, because this of course is another big issue, and we didn't had a chance to cover that topic yet. But yes, recover from failure is always a challenge in in computer systems that with large number of hardware components and the servers. Okay, all right. So right, and at the end we mentioned another important. So in terms of map reduce, it introduced and also another not really new, but it's a trend for data processing, is the idea of moving process to data. It is different from the architecture or the thinking for data analysis before, because in the past we said we separate data storage system and the data, the computing system. So the data has to be loaded from the storage system to the compute nodes before data processing. But this may not, it become less efficient and become a bottleneck to transfer the data. So another key idea from MapReduce, or from the overall the MapReduce platform, not just MapReduce, but the MapReduce with the distributed file system. That's an entire new. No, what they try to achieve is to combine those two systems together, so that you can depends on your data location to decide where to launch my worker or process, so that the data can be retrieved from the local machine. Okay, so that's significantly reduce the amount of network traffic and your needs for network bandwidth. Okay, so that's why usually people will install MapReduce systems on top of a distributed system like HDFS. Okay. Okay. So I think we will get a better idea when we have a lab, so you can actually issue some command and look at how those system components work. Then you can have a better idea, how what exactly that means by having two distributed system installed on a single cluster. Okay, so basically, you can allow the worker for storage and processing at the same node. So that's why we can reduce the network traffic. Okay. All right. So finally, we give you a concrete example to look at the process in another angle, from how the whole systems work, not just the code, not just the algorithm, but how the framework, the distributed system work for handling a MapReduce job. Okay. Okay. So as you can see, we're given a user program, say a MapReduce program, written by the programmer and submit to this distributed system or cluster. And you want to use this program to do a workup on the file, right, which is supposed to be huge and divided to several chunks on the distributed system, distributed file system. Okay. So what happened is just like our MPI cluster is the same thing. We have a master, we have a scheduling queue. So your program has to be submitted to the master, the scheduler. Okay, and in that, the scheduler to decide how to run your program. And in this case, even more complicated, because your program consists of a mapper task and reducer task, and they have to follow the MapReduce workflow to complete the whole computation, right? So say we have total of 4 machines. The first machine, just as a head node, only install the scheduler, the master. So it's not for computing. Okay, and so your map job, the the number of map tasks from your program actually is decided by your file size. Okay, because the goal we want to achieve is to schedule the process to data, right? Move process to data. So it all depends on where your data is located and how many machines have your data, right? So in this case, we say this file consists of 3 chunks. So supposedly they are stored on 3 different machines. So the scheduler, the master, will actually first ask the distributed file system to know where those 3 chunks stored, and then dispatch or launch the map task on each of those machines. Okay, and for each chunk, you have many records, right? So those records will iteratively um, send it to the map function to do the mapping. Okay, so the map function actually will be iteratively called on each of the record of this chunk. Okay, so the map task basically try to call the map function on each of the record. Okay, all right. So that's why you can see we have 3 machine and 3 map tasks. It's all decided by the file size. Okay, so it's not controlled by the programmer at all. Okay, okay, and then you can see this is the important concept here. Okay, so the reason to do this is because we want to have a local read, right? Uh, to read the data from the distributed file system to the map tasks. Supposedly, it should be located on the local machine. Okay, but as a matter of fact, it's not necessary on the local machine because the scheduling decision is just a preference. Okay, so you will try to first schedule the map task to the machine with data. But as you know, this is supposed to be a cluster shared by many users. So there may be many other jobs running on this cluster at the same time. So it's not guaranteed the machine you want to use is available, right? It may occupied by other mapper or reducer tasks as well, because a machine can store, right, a large number of data chunks. So it's not guaranteed the machine you want is available. So if it's not available, it's possible the scheduler will schedule your map task to some machine that is available but without your data. And in that case, your data can still be accessed because HDFS is a distributed file system. So supposedly you can read, write, or access your file from any machines, right? It's a distributed system. Okay. However, in that case, the data does need to be transferred from his store location to your mapper task location. So it's a preference, and the reason is sometimes if you want to enforce a strict data locality, means you only want to schedule the map task with on the machine with data. Then it's possible you have to wait, right? You have to wait. You either have to wait until the machine is available, or you can run immediately, but you need to transfer the data. So it's all about the waiting time, the trade-off between the waiting time and the data transfer time. Which one will be longer? Okay, so it's a trade-off. So it's a decision made by the scheduler. Okay, all right. And then after the map task, we will generate those intermediate key value pairs, right? And those key value pairs will be, as you know, send it to the reducer. Okay, so you see there are 2 buckets here because in this case, assuming we want to launch 2 reducer for this job, so we have to partition those intermediate keys to one of the reducer. Since we have 2 reducers, that's why you can see we try to put them to different bucket, and the key in the first buckets will be sent it to the first reducer, and the key in the second buckets will be sent to the second reducer. Okay, so that's why you can see that's why we have 2 buckets here. It depends on how many reducers you have. Okay, so different from the number of mapper, the number of reducer is decided by the programmer. Okay, so you can set it to any numbers. As you can imagine, if you have more reducer, supposedly you have data parallelism, right? However, more number of reducer doesn't guarantee better performance. The reason is that if you have more reducer, then the amount of data transferred to each reducer will become smaller, right? And for network transfer, usually the smaller the size, the less efficient it is because you have some constant over time for like data latency or connection initiation. So if you transfer a large chunk of data at once, it could be more efficient. Okay, you will suffer less from those constant overhead. Okay, and another reason is the reducer. If you have more reducer, but it also depends on how many machine you have, right? So say you only have, like example here, we only have 3 machines for computation. So if you launch 4 reducers, then 2 of the reducer cannot physically run at the same time anyway. So it all depends on how much resources you have as well. So create more process doesn't always guarantee better performance, right? Okay, so that's why how to control the number of reducers is a tuning knob, a performance tuning knob in this framework. Okay, and as you can see, assuming we have 2 reducer, then what happened is after the mapper generate their immediate key value pairs, uh, the mapper will temporarily store the key value pairs on its local local node. Usually it's in the memory because that's faster, because you're going to read out right away. So you will prefer to store on the memory. But then again, MapReduce the strengths, the key strengths for MapReduce is it can handle arbitrary amount of data. Okay, no matter how large is your data, it never runs out the memory. And the reason is because he only dealt with one record at a time. So same thing here. You can choose to store this temporary result on the memory, but again, you may have limited memory. So if your memory is full, then the mapper will actually store those intermediate results on the disk, on the local disk, on the local file system, not the distributed file system, because distributed file system could store the data on any machines, right? Then that may cause a remote write. But here we want to guarantee it's a local write. So it's actually written to the local file system. Just a temp file in short. Okay. All right. So after all the mapper complete their tasks, then they will notify the master. So the master can launch the reducer according to the number of reducer requested by your program. Okay. And then the reducer will fetch the data from all the mapper, right, to collect the keys for the reducer. Okay, so that's why we have buckets. Okay, all right. So unfortunately, for this step, most of the time they are remote read, and it's cannot be avoided. The reason is because the key of a reducer definitely will come from multiple mappers, right? Because you don't know where the key distributed in the file. So it's always possible that the key is distributed across all the mappers. So you will have to remote read those data for the mapper that's not on the same node as the reducer. Okay, like this case, only the data from mapper 1 to reducer 1 can be a local read. But it will be remote read for the other mapper. Okay, so you can imagine this is also the main performance bottleneck for MapReduce system, because this is the only step that must involve remote access. So you will need network bandwidth. Okay. However, usually this bottleneck can be mitigated or reduced because for most of the application uh, for MapReduce is try to extract information, right? So after the map phase, after the mapping function, the amount of information here supposedly should be much smaller, right? Comparing to your original file or the raw data. So this remote read cannot be avoided, but the amount of data that needs to be read remotely usually is already much smaller than the original data size. It's not always the case, but that's the the general case, and that's the case that MapReduce can work very efficiently. Okay, all right. So sometimes MapReduce doesn't work well because maybe you just try to have the same amount of output data to the input data. So that means you will involve lots of remote read. So uh, that may cause your performance to drop. Okay, or it may take a long time to process the data. Okay. All right. And finally, the result of each reducer will write it out to the distributed file system, right? So that the input file and the output file can all store in our data repository, the HDFS file system. Okay. And again, because you write it to a global file system, distributed file system, so that means whatever the content you write it out could be stored on multiple machines. Okay, so this might involve some remote write as well. Okay, but this is also avoidable because as you know, the HDF file system will replica your data with 3 replica, right? And store on 3 different machines to ensure data reliability with to avoid data lost. So of course, any data write to this file system needs to be write on different machines. So involve remote write. Okay. Okay, but usually one of the copy will be created on the reducer node. So one of the copy should be a local write, but the other 2 copy will be remote write. Okay. And also to avoid synchronization between those or communication between reducer. So actually for MapReduce, each reducer will generate an individual output file. Okay, so that's why there's no coordination required between reducers at all. But as you can imagine, in some case, you like this word count, right? You can see the output consists of 2 files. So one way, if you want to have a single output file, then you have to do a merge sort, right? To merge those 2 output files together. And then you have a global sorted and single output file. Another way to do that is you can force or can choose to have only a single reducer. Then, of course, all the data will be sent to that reducer and write it to a single file. So that's another way to generate, directly generate a single output file. But the downside of that approach is your your parallelism is only 1, right? So you didn't parallelize the reduce function. So it may take longer to do the reduction. Okay. All right. So so that's all the details for MapReduce. Okay. This is very critical because this is exactly what you need to do for your final homework. Okay. So for final homework, not only we would like you to master MPI and thread programming, but also to understand, at least use MapReduce example, right? To understand how a distributed computing can be a framework could be designed, and how can you realize that design by implement it on your own. Okay. So in homework 4, the last homework, you have to create those master process, worker process, and communicate as we explained over here. Okay, and you have to write it with a MPI. Write it in a MPI program. Okay, so a bit more complicated than the previous case because that's only about the algorithm. But here you need to have a understanding of the computing workflow. Okay, and see if you can to use all the knowledge you have and implement this workflow as the MPI program. Okay, all right. I think after that implementation, we can that's we also want to make sure you fully understand how MapReduce work. Okay, because you need to know how they work first, then decide how you're going to implement it, right? Okay, and you will find out that implementation is probably a bit more complicated than the previous homework. Okay. All right. So again, please try to start the homework early and manage time well so you can complete the final homework and the final project. Okay. All right. So finally, we want to introduce some application of MapReduce. We said MapReduce is very important because actually it's a tool uh, designed to build the search engine of Google. So you can see how important it is. Actually, Google search engine is depending on this MapReduce framework. Okay, and the search engine is actually, in general, it's a problem of information retrieval. So you can see there are a class of a problem that could be solved by MapReduce. Okay, so that's why it was so important, right? Information retrieval is one of the key of data mining and big data. Okay, okay. So what is information retrieval? In short, in general, it's referring to any problem that we try to extract information out of data, right? And the form of the data could be arbitrary. So that is the variety property of the big data problem. Remember, so not only just the volume. We already explained how MapReduce solve the volume, right? You can process any size of the data with limited memory because it never store anything in the memory, or the memory usage of MapReduce is never proportional. It's a constant. It's not a proportional to the problem size. So that's why you can solve the volume problem. But how about variety, right? Variety means that uh, the system should allow the user to write a data analysis program to analyze the data in any format, right? And so MapReduce, it can do that because it only try to store and process the binary data, some raw data. So how you interpret those data, as a picture or as a video or as documents or image, it all depends on your mapper function, right? How you would like to map that information. So that's why MapReduce can solve the variety problem. Okay. Okay. And so back to here, the IR node, it just try to, in general, it try to extract information in any kind of data. Okay. And so here, as example, specifically, we consider documents, right? And the information we try to extract, are some words or terms. Okay. So for example, one could search some document with some term. Okay. Okay. All right. So how could we do that? Okay. So the basic step and the concept is, as you can see over here, right? You have datas, those documents, and the documents needs to be represented by some representation, right? Uh, then the user who want to extract or search information out of the data will try to also use the same representation, so that you can use the same representation to decide whether they have matches to the search criteria. Okay, and specifically for document, the representation we use usually is the term, right? So we know documentation consists of those terms, and the user can use the term keyword to search the document, right? And you can see this is just one way to realize the idea, right? It doesn't mean this is a perfect way, because you can see term is easy to determine, but you also lose lots of information, right? For example, the tragic story, then what does it really mean, right? It has some meaning to the term. But if we just try to do the matching based on whether the term is the same or not, then we may lose the information of their meaning. The meaning behind the word is lost in this translation. Okay. So how to decide the representation is another difficult problem. But here, of course, as you know, the search engine today mostly is based on this representation. So you can search very quickly, efficiently, but may not be very accurate at some time, right? Okay, so how to realize that information retrieval by the system, by the computer. So what we would need to do is to build index, okay? Because you have so many data, and the query can consist of any terms. So how could you efficiently find the document with the term, right? So that's why we need to build index. Just like we have dictionary, so you can, when you try to look up some word, you can look up the dictionary, right, and find the word very quickly, because the dictionary is, they order the words by their character in alphabetic order, right? So same thing here. Of course, first thing is to translate the document into some representation, and which of would be term, of course, and then try to build an index based on those terms. And then the query part will try to represent the query using the same representation, and then try to do the comparison, right? To check out this index instead of search through the documents. And so it can quickly, hopefully you can quickly identify the document that match the query, and then return the result. Okay, so this is the basic step, right, to do information retrieval or to search some documents. Okay, and what you need to know is, right, of course, the computation happens for building the index and resolving the query. And those two things actually should be performed at different step and stage, because for index building, it should take place offline. Means you can build those index before the query arrive, right? And building the index may very time consuming, because you definitely have to scan through the data at least once to generate the index. So index is a classic big data problem, and this also fit the purpose of MapReduce, because this is a data analytic work. You have to analyze the data and process through the whole data set. So it's involve a huge volume. So it is what the MapReduce designed for, right? On the other hand, to query the index is actually not suitable for MapReduce. So usually it's still use the traditional database to do the query search, because the index supposedly could be loaded to the database, right? And the size of the index should be much smaller than the data. So supposedly we can load it to the database, and the query must be processed online, right? So it cannot wait. So it requires latency. So this part should still take place on a database, a traditional solution like database. Okay, so the whole solution actually involve two phases, and the MapReduce is used to build the index, not used to query the index. Okay, all right. So this is how a search engine is built. MapReduce is just part of this solution. Okay, all right. So let's just look a bit deeper, and eventually we will show you how this index could be built by MapReduce. Okay, so this is what we mentioned. The representation is using the bag of words. This is the simplest way, but very efficient way to deal with documents, right? And of course, it's not as simple as that because some of the words are more important than the others. So actually, usually we have some weight associated with those terms. And supposedly, we should consider those weights when we try to compute the correlation or the, the the fitness between the query and the data, right? Okay. But overall, this is still a better representation, a more efficient uh, representation for searching because usually the word is well defined and it's independent to the documents. Okay, and so you can count those words independently from each document. Okay, so after you have those words right processed from the document, there's actually a couple of steps you need to do as well, right? The first thing is tokenization, right? To find out what are the terms. And some of the terms, they are like this case, it actually should be separated into two terms instead of one. So you have to do some data pre-processing as well. And you might want to drop out some right meaningless word, right? Like a, and, is, etc. Okay. And finally, like search engine, sometimes you have to deal with the language, different languages. So you have the normalization to make sure they looks the same, right? To reduce your problem space, right? So all those things also need to be considered in this approach. But many other complex problems like syntax, semantics, right, knowledge, all those are not considered in this representation. So at least it simplify the problem in certain degree. Okay, and then we simply just use the term to build the index called the inverted index. Okay. All right, so we run out of time, but next time we will introduce what is an inverted index and how it could be implemented by MapReduce. And inverted index, this is a classic example for building search engine. And in the future, if you try to deal with those information retrieval problem, I think if you know how this is done by the search engine, you probably could apply the same idea or the same solution to solve your problem as well. If you really want to build a distributed search engine or distributed solution for information retrieval, okay, this will be a good example. Okay. All right, so that's it for today's lecture, and we will continue on next Monday. Okay, okay. Questions?